So the last topic we're going to cover regarding waves is shock waves and sonic booms, and it's kind of a small little topic. Come on, there we go. So we've already talked about the Doppler effect, and that's one thing that happens when you have a moving source of sound. But if that source is moving really fast, faster than the speed of sound, then you get some other things going on. So what these images are showing here is the reddish pink dot thing here is the source of the sound waves, and if that object, the source, is stationary, then the waves are just going to propagate out in all directions. But if that object is moving, this is what we saw with the Doppler effect, you'll get higher frequency waves over here and lower frequency waves over here. But if we keep speeding up to the point that we equal the speed of sound, each new wave on the right hand side is just going to keep adding pressure to this wave front here. This side is still just going to be shifted to lower frequencies, but you're going to get this buildup of pressure here. And even if you exceed the speed of sound, then you still get pressure building up along this wave. You're going to get constructive interference on this edge of each of these sound waves that are propagating out. So you get what's called a shock wave. And those things are what are responsible for sonic booms. And they make some cool pictures and whatnot too. So let's look at this idea one more time, but now animated. So here the source of the waves, whether it's a sound wave or otherwise, is moving slower than the wave propagation, and so you get this Doppler effect. Here the wave speed equals the speed of the source. I guess on the last one we called this the speed of the object. I should have been consistent with that, sorry. And here the source is moving faster than the waves. Okay, so a couple of pictures where that can happen. This can happen in water. Water waves are quite slow, so in order to exceed the speed of water waves, even a duck can do that, and you end up with this nice cone, this shock wave that is due to the fact that the duck here is swimming faster than the propagation of the water waves. This is why you get a wake behind a boat. It's the exact same thing. Now we can get these shock waves in the air as well. This is a jet car, rocket car, and you see the air is distorted right here. These are shock waves in the air. So in this case, to get shock waves in the air, you have to be traveling faster than the speed of sound. And a couple other pictures. Usually it's airplanes in the air that are doing that, and you get a bunch of different shock waves, but you tend to get a major shock wave right at the front here, and then you tend to get a good shock wave here in the back as well. And so the idea is if you have somebody on the ground, when this airplane flies over, both of these shock waves will hit it, and that's what you hear when you hear a sonic boom. So it's a misconception that the sonic boom is related to when the airplane actually goes from slower than the speed of sound to faster than the speed of sound. That's not the case. As it's flying, there's this shock wave, and anybody who gets hit by that shock wave will hear the boom. So in this picture here, this person has heard both of the shock waves already. This person just barely heard that one and hasn't heard this one yet. Usually they're so close together you can't distinguish the two separate booms because the speed of the airplane is quite fast, so these booms are really close together in time. But this person here at location C hasn't heard the sonic boom yet. Now we do call it the sound barrier. If I go back a little bit here to this picture, you build up this pressure wave here when you meet the speed of the waves, or for airplanes the speed of sound. And so the airplane actually does meet some resistance at this point, and so it takes some extra energy to exceed the speed of sound. Once you're going faster than the speed of sound, there's less pressure resisting. So breaking the sound barrier refers to the object itself. There is kind of a barrier to go faster than the speed of sound, but that's not what causes the boom. The boom is just when that shock wave happens to reach some other observer. Alright, so that's it for this time. Nice and short. Over and out.